Welcome to Independence, when we are dealing with probability. So today we're going to learn about independence and work through some examples. Now, two events are independent if any of the following equivalent statements are true. If we find that the probability of A given B equals the probability of A, that shows us that the probability of A is not affected at all by what happened with B. So that would be one way we could show that A and B are independent. If we find or show that B given A equal the probability of B, once again, that's just telling us that the probability of B is not affected at all by what happened in event A. Also, if we find that the probability of A and B equal the probability of A times the probability of B, this is another way to show that the two events are independent. Now, if we're told our events A and B are independent, then all three of these will be true, and we can use them to find probabilities. So note, what does this all mean? It means that the probability of the occurrence of one event has no impact on the probability of the occurrence of the other event. So let's look at this example. A production lot of 850 parts contains 50 defective parts. Now, 2 parts are selected at random, but the first is replaced before the second selection is done. So we call this sampling with replacement. So let A denote the event that the first part is defective. What would that probability be? Well, that's nice and easy. There's 50 defective parts, and there are 850 parts to choose from. So if B denotes the event that the second part selected is defective. Now remember, we're sampling with replacement. So that first part, no matter what it was put back. So once again, we have 850 parts where 50 of them are defective. So the probability of B would be also 50 over 850. What's the probability that the second is defective given that the first one selected was defective? In other words, the probability of B given A. Well, not using formulas, thinking about the situation, what's the probability of B given that A occurred? Well, given that A occurred doesn't affect B at all because we put that defective part back. So the probability of B given A is just 50 over 850. So now what's the probability that both are defective? Well, this is kind of jumping the gun right here. How did I get that? That's how I would find that. The probability of A and B. Well, we know when we learn conditionals that the probability of A given that B occurred is the probability of A and B divided by the probability of A. So I could always find the probability of A and B by solving this equation for the probability of A and B. It would just equal the probability of A times the probability of A given B. But in our example, that's not, given what A and B are, that's not what I was looking for explicitly. So then I look for the other way that we know about conditionals. I could just say the probability of B given that A occurred. Well, that's the probability of A and B divided by the probability of A. So solving for A and B, I'd have the probability of A and B equals the probability of A times the probability of B given A. Now that's the one that I want because I've got the probability of A and I've got the probability of B given A. And I can use that to solve for A and B. When I do that, look what happens. So that's the probability of A times the probability of B given A. But the probability of B given A, it just equals the probability of B. And that's how come I could use this, because A and B are independent of one another only because I sampled with replacement. So I'd have 50 divided by 850 times 50 divided by 850, and I'd have my answer. Let's look at another example. Now, the data shows, what we're going to use is use the data to show whether the events are independent or not. So I want you to look at what we're doing and see if our events D and F are dependent or independent in our first example, and then do that again. See if our events D and F are dependent or independent in our second example. So just stop the video, and you know the three different rules, or the three different things that occur when you have two events that are independent. You need to check to see if that is true. So let's look at this. The probability D, given that F has occurred, see how I have highlighted this? We don't care about the no anymore. So we're not looking at the total anymore. We're looking at just having surface flaws. So given that we have surface flaws, what's the probability of being defective? Well, we have 10 out of 40. Now, going to the second one right here, the probability of defective. Well, here's defective right here. Now we're looking at the whole sample. We don't have a given. The probability of defective is 28 out of 400. Since the probability of D does not equal the probability that D given F, D and F are not independent. Now let's look at the second example. So I look at the second example. The probability D given F. Once again, I'm just looking at this. Don't care about that in this probability of D given F. We have 2 out of 40. Or 1 out of 20, however you want to write it. Now let's look at the probability of being defective. The probability of being defective, now we're back in the full sample space of 400 and 20 out of the 400. Well, once again, if I do this, this equals 1 out of 20. We find that the probability of D given F equals the probability of D. Therefore, D and F are independent of one another. Okay? Now, D and F are not mutually exclusive, but they are independent. So just because you're independent does not mean that you're mutually exclusive. So looking at our next example, once again, I'd like for you to stop the video, work on the problem, then work on it. We'll work on it together. Now we're looking at this time at 850 parts. It contains 50 defective parts. 2 parts are selected at random without replacement, meaning I have the part in my hand, then I select the other one. So the probability of A is 50 out of 850. Now, let B denote the event that the second part is selected. The second part that you select is defective. Well, now I have one less. I have 849 out of 50. So when I look at this, the probability of B, that the second is defective, is going to look like the probability of B given A times the probability of A, plus the probability of B given A prime times the probability of A prime. That law of total probability. So using that law of total probability, remember, we have event A. Either we're going to have a defective part or not a defective part, okay? You could either choose a defective part on that first pick or not a defective part, which your sample space has the defective part and not defective parts. B is the event that the second part picked is defective. So if I want B in here, this is B intersect A, and this little area is B intersect A prime. So we know that we can rewrite B intersect A as the probability of B given A times the probability of A. We know we can rewrite B intersect A prime as the probability of B intersect A prime times the probability of A prime. Remember, that's how we got the law of total probability. So I put in my numbers. The probability of B given A, we just found out 49 out of 849 times the probability of A, 50 out of 850. So what's A prime, or the probability of A prime? It's going to be 800 out of 850. So I put that in here for probability of A prime. And then the probability of B given A prime. Well, if the probability of B given A is 49 out of 849, then the probability of defective, given that it wasn't defective, would be you had 50 defective, so the probability of B, given that the first part wasn't defective, you have 849 in your sample space because one is taken out, but you still have 50 defective parts left. That's this number right here. And I multiply that by the probability of A prime. And so I get this number right here. The probability of B, putting them together, is 50 over 850, which is the same as the probability of A. Since the probability of B given A doesn't equal the probability of B, then A and B are dependent. If events E1, 2, all the way to EK are independent, they're independent if and only for every subset of these events, the probability of E1 and E2 and E3 and EK equals the probability of E1 times the probability of E2 times all the way to the probability of EK. Now, if E1 and E2 are independent, E2 and E3 may or may not be independent. It must be stated or known that all events are independent in order to say that the probability of E1 and E2 all the way to EK equal the product of all their probabilities if E1 through EK are independent. So let's look at a specific use of independence. We're going to look at what's called circuit problems. Now we're going to look at the circuit operates only if there's a path of functional devices from left to right. So from this way to this way. The probability that each device function is shown on the graph. So if we call this device 1, or the left one, and this is the right one, the probability that the left works is 0.8, the probability that the right works is 0.9. Now assume that these devices fail independently of one another, okay? Meaning that whether this fails does not at all affect whether this one fails. So they're independent of one another. What is the probability that the circuit operates? So first of all, what type of problem are we dealing with? Are we dealing with a union, addition, Bayes' theorem, etc.? Well, we're dealing with whether the left and the right work. So it's an intersection problem. Okay, so we're looking for whether the probability of left and right, that they both pass. Since they are independent of one another, then we would find the probability by the probability of the left times the probability of the right. So it would be 0.8 times 0.9, or I have a 0.72 chance of the circuit operating. The probability that a wafer contains a large particle of contamination is 0.01. Now let the probability EI denote the event that the ith wafer contains no particles. What is the probability of EI? Now, we would assume that one wafer won't affect another wafer. So the probability that any wafer would have contamination would be 0.01. Due to independence. Then the probability that EI doesn't have any particles equals 1 minus the probability that EI contains particles. We'll call that prime. So that's 1 minus 0.01, or 0.99. So if 15 wafers are analyzed, what's the probability that no large particles are found? Please work on this, pause, and then we'll come back and work on this together. With this, we would say that the probability of the first particle times the probability of the second particle having no large particles found. That's E2, all the way to E15. Well, since all of these have a probability of 0.99, then the probability, if 15 wafers are analyzed, what is the probability that no large particles are found in any of them? Would be 0.99 to the 15th power. That's 0.86 probability that if 15 wafers are analyzed, no large particles are found. Now let's look at another circuit problem, but this is a parallel circuit problem. Now let's look at this problem. The circuit operates only if there's a path of function from the left to the right, just like before. The probability that each device functions is shown. Now each device fails independently. So this device fails and this device could fail independent of one another. So we're going to call this the top. So the probability of the top working is 0.95. The probability of the bottom working is 0.95 also. Now we say that T and B denote the events of top and bottom devices operating, like I've just shown. What's the type of probability problem? This one. What is the type of probability problem we have here? It is not an and. It's not whether the top and bottom work, because think about electricity. Electricity could flow and go through the top and go down there, so that would make the circuit work. I could do this. The electricity could go through here and the circuit would work, or both of them work and my whole circuit would work. So I've got quite a bit here. This is an or problem, this, or both. So how would we work that? Well, we'd say the probability that the device operates is the probability of the top or the bottom working. And we know our calculation for that. It's the probability of the top plus the probability of the bottom minus the probability of the top and bottom, just using our formula for union. And that is one way we can find the probability that this circuit operates. But there's also another way to find out another way to find the probability that this circuit operates. Can you think? So this is one way to do it, but it's a little bit more work. There's a faster way to do this. The probability that it operates is the same thing as the probability is rather 1 minus the probability that it does not operate. And for it not to operate, that would mean that this circuit doesn't work and that circuit doesn't work. Okay? That would be an and problem, and we know how to find that since top and bottom are independent. This would just be 1 minus the probability the top doesn't work times the probability the bottom doesn't work. And we know those probabilities. The probability that it doesn't work on the bottom is just 1 minus 0.95 or 0.05. The probability that the top doesn't work is 1 minus 0.95 or 0.05. And we can easily solve this equation by 1 minus multiplying 0.05 times itself and do that subtraction. So two ways to get to the same answer. One might be easier or faster than the other. So in looking at that, if we went the straightforward way, we'd say 0.95 plus 0.95 minus multiplying those probabilities together, and we'd get 0.9975. And again, if I had to use the other method, the circuit working, as 1 minus the circuit not working, I would have taken 0.05 times 0.05, and I'd subtract that product from 1, and you get the exact same answer. Now, a third way to look at this, and this is a little more time consuming or a little more computation involved, is for this to work, we could say the top working, but the bottom one not, okay? This one right here. So that means the probability of the top 0.95 times 0.05. Or the probability the top doesn't work, but the bottom one does. That's the probability of the top not working, probability of the bottom working. Or, like we said, I could have the top working and the bottom one working, and that would be this one here, top and bottom working. And my answer, again, if I work through all of this, would be 0.9975. So we could look at it as the union of these three different ways that the circuit could work. So again, another method for finding that probability. Which one you use is how you see the problem. Now, a simple problem like this, you might want to go the more simple way, but when it gets more involved, sometimes it's not as easy to see. So knowing that you have all these different ways to go about getting the same answer is a bit comforting. So please stop the video once again. You're going to see here a combination of both unions and intersections and trying to find whether this circuit works. So please stop the video and try to get the answer on your own, and then I'll come back and work on it with you. Well, I can take this as this working, and then this one working. So this whole little unit here working, and this unit working, and that unit working. So if I say this is, we'll call this unit 1, unit 2, unit 3, the probability that my circuit works would be unit 1 and unit 2 and unit 3 working. Well, unit 3 is easy, it working. I know that probability pretty simple. But I'm going to have to think about problem for the probability of unit 1 plus the probability of unit 2 plus the, not plus, but times, of course, because they're independent of one another. And as I said, I already know that probability is 0.99. But I have to find the probability of unit 2 working. Well, this is it's parallel. So I know I could find it. My preferred method is to use the complement. So we look at the probability of that second unit right here working, what I'm calling the second unit. It's 1 minus it not working. And that's just like the problem we just finished. 1 minus it not working would mean this and this not working. So not working would be 0.05 times 0.05. 1 minus 0.0025 or 0.9975. Now, the first unit here is a little bit more involved, but not by that much. So I'm going to use the same method I used to find unit 2. So the probability that unit 3 works is 1 minus one minus the probability that it doesn't work. So this one not working is 0.1, 0.1, 0.1, of course. And so with that, I would say the probability is 1 minus 0.1 times 0.1 times 0.1. So the probability of this first unit working, this first parallel circuit working, is 0.999. So to find the probability that this circuit works, I just take 0.999, I multiply it by 0.9975 times 0.99, and you get 0.9865 if I go to 4 decimal places. Now note, this is just one way to do the problem. I showed you 3 different ways to do parallel circuits. So there's many mixing and matching for ways to solve this. I just try to do it as quickly as possible. So this is just a look at independence, how we use it, and how we use it in different situations. But there's more than this. Thanks so much for watching.